Hi, welcome to Chem with Chem. In this session, we're working question 4 of the May-June 2015 edition of the CSEC Chemistry Paper 2, still a mouthful. Don't forget to like, share, and subscribe. You don't want to miss other sessions like this. You don't want to miss other questions like this, plus the full workout. Let's begin. This question epitomizes the application of chemistry, not just in the lab to prepare things, but just in the home and in general. Let's check it out. Tums and Epsom salts are items commonly found in most household medicine cabinets. Calcium carbonate is the main active ingredient in Tums, an antacid used to relieve heartburn, acid indigestion, and upset stomach. Tums is a registered trademark. I don't know if you know that. Tums. Right. So it's a registered trademark. And Epsom salt, as I won't say as we know, Epsom salt is hydrated magnesium sulfate, but we'll get into that a little bit further. Let's see what they're asking us for the first part. Describe one method for the preparation of dry calcium carbonate in the laboratory. In the answer, include an equation for the reaction as well as the steps that are involved in its preparation. So, of course, we always ask when we're preparing a salt, is the salt a soluble salt? All right, we're not going to go through yes or no. We just want to reach if it's an insoluble salt. Well, in this case, it is an insoluble salt. And a way to prepare an insoluble salt is to use 2 salts that are soluble, that each contains the ions in the insoluble salt. So here we will need, we're trying to make calcium carbonate. So we will need a soluble salt that contains calcium ions, and we're going to need another soluble salt that contains carbonate. We're going to need those in solution. So we're just going to start with the reagents, straight up the salt solutions of those soluble salts. So all nitrates are soluble, so we can work with calcium nitrate, and all sodium, ammonium, potassium salts are soluble, so we could work with sodium carbonate. So we would need to mix, and we're going to use amounts. So in step 1, we'll have to mix our reagents. Carefully deliver or carefully add 25 centimeters cube of aqueous calcium nitrate solution into a beaker containing 25 mils of aqueous sodium carbonate solution. Then we're going to stir with a stirring rod. There needs to be mixing so we can get the reaction occurring. All right. When this happens, we're going to get our precipitate forming. So the next step would be to carefully filter this mixture So we carefully filter this mixture using filter funnel, filter paper, and conical flask. We will retain and rinse the precipitate or the solid with minimum amount of distilled water. And in number 5, we can allow it to air dry pat in paper towel and allow it to dry in the air, allow it to just dry like that in the air, or we could put it in the oven on low heat until dry. Of course, we would have to include the equation to get the remaining marks. And this is the balanced molecular equation. If we had the ionic equation, that would be fine, but this is more complete. Part 2 of A. The main ingredient in Epsom salts is magnesium sulfate. List one use of Epsom salt. All right, Epsom salt. For one, there was a prank. I know of a prank where this was used. Oh my word. So it's a laxative. It's used in the treatment of arthritis. So it's a good muscle relaxer. Hence, it's used to soak. Persons use it to soak their feet after a long day's work, after they've been standing for a while. It's used to treat the swelling of joints, etc. All right, so they asked for 2, we've given like 4. Part 3 of A. In order to effectively use Epsom salts, it is usually made into a solution. Explain why water molecules are able to dissolve Epsom salts. So first things first, they said magnesium sulfate is in Epsom salt. And magnesium sulfate is an ionic compound. Water is a polar compound. Water is a polar substance. Like dissolves like. So water which is polar can dissolve ionic substances. Like dissolves like. Magnesium sulfate is an ionic compound. Water is polar. Polar substances dissolve ionic substances and other polar substances. So the slightly negatively charged oxygen atoms in water, they interact with the magnesium ions in the lattice structure of the magnesium sulfate. And the slightly positively charged H atoms interact with the sulfate ions, resulting in a disruption and breaking up of the ionic crystals. So like dissolves like, and we know that water, which is polar, can dissolve ionic compounds, and this is how it happens. So that's why water is able to dissolve Epsom salt. And we can soak our feet in it after we've been standing for a long, hard day. Part B, for 6 marks, which will make up our 15 marks. When magnesium ions are present in natural water, it is referred to as permanent hard water. Describe how permanent hard water is formed. include balanced chemical equations with state symbols to illustrate this process. This is one of the areas, or this is one of the areas that I consider to be a counterintuitive concept. Because for one, when we think of hard water, I guess if we switch off the chemistry part of our brain, when we think of hard water, we probably are thinking about water that is probably tough. I don't know if people think of it like that. But the funny thing is, hard water is referred to as hard when there are calcium, Ca2 plus, and magnesium ions present in it. So it is said to be hard, quote unquote hard, right? So that's that. The other thing now, if we can remove or capture, inactivate, or arrest, those are some of the terms used. If we can remove Ca2 plus and magnesium ions from the water, then that's called softening. But we're not going to look at water softening. No, we're going to look at that in another session. Stay tuned. So describe how permanent hard water is formed. Include balanced chemical equations with state symbols to illustrate this process. So let's look at how permanent hard water is formed. So when we look at temporary hardness, we get that coming from calcium and magnesium ions that would have dissolved from calcium carbonate and magnesium carbonate rocks. That's water in the presence of carbon dioxide giving us calcium hydrogen carbonate. Now, these are aqueous, but when we heat calcium hydrogen carbonate, it breaks down, it decomposes to give us back calcium carbonate, which is a solid. So this concept of permanent hard water, or hard water in general, is counterintuitive, because water is considered hard because it contains calcium 2 plus and magnesium 2 plus ions. So when we remove those ions from the water by whatever process, whether we're going to treat it with washing soda, slake lime, or whatever means, whenever we remove the calcium 2 plus and the magnesium 2 plus ions, then the water is considered soft. It's a little counterintuitive, because when these ions precipitate out, they form a solid. And I normally say you're either part of the solution or you're part of the precipitate. Now, precipitate is a solid. So when you look in your kettles and you see the white scales that is built up, the built-up of the white scale means that the water would have been softened pretty much, because those calcium ions have now been removed, because they would have been in the presence of, they would have been in the form of calcium hydrogen carbonate, but upon heating, they decompose to form the solid calcium carbonate or the solid magnesium carbonate. All right, so it's a little counterintuitive. So let's look at how permanent hard water is formed. And this is just the prevalence of Mg2 plus ions based on this question. So permanent hardness of water is caused by calcium and magnesium sulfate dissolving from rocks like gypsum. In the introduction, they gave us when magnesium ions are present in natural water, it's referred to as permanent hard water. So we're going to focus on the presence of magnesium ions. So we'll start off by saying water passes through rocks like gypsum, which contains magnesium sulfate. The solid magnesium sulfate dissolves in the water, giving aqueous magnesium sulfate. Mg2 plus ions are present in the aqueous medium, and so that is permanent hard water. This is magnesium sulfate. It cannot be decomposed or cannot be heated to form a precipitate. So the Mg2 plus prevails, and so we say it's permanent hard water. And as I said, this concept in and of itself is counterintuitive. So let's just write that, and then we'll just look at our equation. So as water passes through rocks like gypsum, which contains magnesium sulfate, which is a soluble salt, the magnesium sulfate dissolves in the water setting the Mg2 plus ions free. And all we would need for this is include balanced chemical equations. Equations here, this part is tricky, which we don't need any trick because this is already a counterintuitive concept. So we would write magnesium sulfate, the solid rock that we mentioned just now. Water is added to that, and we would end up with Mg2 plus aqueous plus SO4 2 minus aqueous. So in a conventional sense, it won't look balanced, but CXC would give the mark if you don't include the water. But this concept is building on part 3 of A above, where we explain how or why water is able to dissolve Epsom salt. So it's the same principle we're building on. So if we put the water there, we don't have to put anything about the water over the right-hand side, because the fact that we have aqueous, is telling us that the water is present, that these ions are in the presence of water. Aqueous meaning aqua. Now, this is for 6 marks. I don't particularly like the question. I don't like the question because it can lead to confusion, not because there is a lot of space, but for 6 marks, and then the fact that they have asked for, they have said include balanced chemical equations, and it's not, question could have been worded include a balanced chemical equation, because to show magnesium sulfate dissolving in water to give Mg2 plus and sulfate 2 minus ions, that's just a one equation. And then this question, I think, is not ambiguous, but it's designed to trick, and this is my opinion. It's designed to trick because temporary hardness, if we're asked to give equations for temporary hardness of water, there are, well, not to give equations for temporary hardness of water, but when we look at the formation of temporary hard water, we have one equation, and then that same equation shows how the temporary hardness is removed, it's treated, or it is removed. So it can be a little confusing. Though for the formation of temporary hardness, it's just the fact is that it's still aqueous magnesium, but for the fact that for temporary hardness, we're looking at calcium, Ca2 plus and Mg2 plus combined with hydrogen carbonate. Despite the fact that they said include balanced chemical equations, this is the only equation that could be used. They would also accept MgSO4, the aqueous magnesium sulfate, which would have been formed when what we have in the first equation here happens. If we show that this gives us Mg2 plus aqueous and Mg2 plus aqueous and SO4 2 minus aqueous, then they would accept that. It's balanced, but it's not supporting all that we've mentioned up top, showing showing the formation, really, how the ions come about, how they just end up in the water like that. They're coming from the solid rock. Solvation is taking place. That's hydration, solvation, SOL, solvation with water. The other one is with the blood. But you get the point. So that's that. Don't particularly like this question, especially because they have include balanced chemical equations. They could have said include a balanced chemical equation with state symbols to illustrate this process. So that is that. This should give us 6 marks. And just like that, we've come to the end of this session. Be sure to check out the other materials on the channel just for you. Couple later.